There we go. Good evening, everybody. Oh, and Janet in the chat already keen to get started, clearly. Hey, everyone. Thank you very much for joining. A big thank you for getting involved throughout today. It's our final session. I'm very much looking forward to it. I won't steal the thunder from Dojo, who are going to kind of like facilitate this session, so I will pass straight over to Sarah to do introductions. As ever with any of these sessions, if you need anything throughout in the chat, just let us know. But yeah, Sarah, over to you.
Hi everyone, I'm Sarah and I'm a back-end software engineer at Dojo who specialises in C# and DevOps. Over to Fruz.
Hello everyone, my name is Foruz. I'm a senior software engineer at Dojo. I have over 10 years experience in C# and .NET, and I'm going to take you through some code after Sarah's presentation. Over to Sarah.
Should we wait a minute or two for more people to join, or should we get going?
I think if you want to just kind of get going, share the presentation, get kind of the intros and stuff done. The way this works is people can watch from the start anyway if they join late. So it kind of like goes back to the start. So we should be all good to go.
Fantastic. Now, hopefully the screen sharing will work properly.
Always the key bit, isn't it? You can be as prepared as you want and you can practice it as many times as possible, but when it comes down to it, how will it go? There we go.
And everyone see the slide saying Dojo, a path to a
Yes.
life. Great. So I'm going to get started, and if there's any questions, please just pop them in the chat, and at the end of the presentation, we will be going through the Q&A. Everyone should have also been given a handout which has on it a glossary and different resources with links to useful websites and examples. So please do look at that if there's anything you're not sure on, so to speak. The structure of our presentation today is that I'm going to go through some slides with you in the theory, then Fruz is going to do a live coding example. I'll then do a bit more theory and then a bit more live example. So let's get started. Now, Margaret Hamilton was the first female software engineer and also the person who coined the term software engineering. She was actually the first programmer to work on the Apollo 11 software, i.e. the moon landing, and essentially heavily influenced a lot of the software engineering principles we follow today. In an interview, she said that the process of building software should be considered an engineering discipline, just like with hardware. And I felt like this was a really important concept and kind of quote from her, because ultimately that's what we're going to be covering today. In your handout, there's actually a link to the full interview, and it was a really inspiring read. So what is code craftsmanship? It's something that's talked about a lot, but we don't often actually properly go into it. Ultimately, code craftsmanship is a set of disciplines and principles to follow, which result in a clean, maintainable, and extendable code base. And essentially, something that's kind of an important thing to really grasp your head around are the pillars of code craftsmanship. Now, I know there's a lot on the screen right now, and we're going to be going through everything on the screen, but don't worry if it feels, like a lot. So the main pillars of code craftsmanship are KISS, which stands for Keep It Simple, Stupid. Dry, don't repeat yourself. Yagni, you ain't gonna need it. Boy Scouts, leave things in a better state than you found it. And tests, continuous testing through small changes. Another kind of big pillar of code craftsmanship is the SOLID principles. Now, SOLID stands for Single Responsibility Principle, the open-close principle, the list of substitution principle, interface segregation principle, and dependency inversion principle. And something that I think is really important is that solid is quite a complex thing to get your head around. We're going to be going into more detail later on about it, but a lot of people find it quite overwhelming. And I also know a lot of kind of experienced software engineers who still sometimes fumble with it. So I just really want to make it clear that, you know, if it feels like a lot, don't worry. Now, what does code craftsmanship actually look like? And it's about ultimately breaking down your problems into small, manageable chunks that can be, you know, almost like quick wins, but manageable is really the key thing there. It's actually also about writing small methods and classes that have one job and utilizing things like helper methods and really kind of figuring out ways to reach that. It's about not overcomplicating the situation. Like periodically take a step back, make sure you've got your, requirements in mind and keeping your end goal in mind at all times so that you don't end up veering off scope. It's about writing tests as well and making sure that you're writing a system that is safe. And ultimately writing reusable and extendable classes and methods through interfaces and abstractions. And for those who don't know, an interface is essentially a contract. So it's often a class with the method signatures in it, but there's no actual implementation, there's no business logic. And what does this actually achieve? Well, ultimately, you have less spaghetti code. And by that I mean code that's messy, it's hard to read, and difficult to maintain. You end up with a thoroughly tested code base where you can actually confidently add functionality and know that you're able to do so without worrying about breaking existing functionality. Your code is physically easier to read, meaning it's easier to understand. And what that means is you actually end up having a really good understanding of what your code is doing and what code that other people have written is doing. Now, we're going to show you some examples of these pillars now, because it's always easier to understand it with a real example. First, we're going to go through KISS, which is keep it simple, stupid. Now, to the left is a classic solution to the known FizzBuzz technical test. For those who don't know FizzBuzz, the idea is that you go through every number from 1 to 100, and you print fizz if the number is divisible by 3, you print buzz if the number is divisible by 5, and you print FizzBuzz if the number is divisible by both 3 and 5. And if it isn't divisible by either, you just print the current number. Now, you might be thinking, okay, this is a very basic for loop. It's written in C#, by the way, as are all of our examples today, but in your handout, there are also examples in Python and JavaScript. Now, on the left, it's just a simple for loop with some if-else, calculations in there. Now, this is a code example that I've used from a blogger called David Omid, who wrote a detailed blog post on KISS, and there's a reference to that in your handout. Ultimately, this is actually the same method, and it has the same outcome. However, it's been written in a kind of fancy, complicated way, and written in such a way that it might visually look better to somebody who's not really doing a deep dive into it. But to properly understand the code, you actually have to really think about it. You might have to try and debug it. You might find that hard as well, and you can't just read through it and understand it. And this is a violation of KISS. The whole kind of concept around KISS is keeping things as simple and straightforward as possible. And from my own experience, it's actually quite easy to violate it when you maybe don't feel, like you're still trying to prove yourself, or you're trying to write stuff that maybe looks more advanced on paper. But ultimately, writing things in the most simple way possible will make everybody's life easier. Now we're going to get on to dry, which is don't repeat yourself. Now, dry is really easy to accidentally violate when you're building quite big systems. You might kind of not realize that code has been repeated, especially when you have multiple people working on it. So it's something to always kind of keep a lookout for. Now, to the right of the screen is a basic kind of mock API. There are two get methods, one to grab multiple objects and then to grab a specific one. Now, both of them log a message depending on whether or not it was successful. And they just write it to the console. Now, something to keep really kind of realize here is that these if-else statements are exactly the same. And in fact, the message within each one is almost identical. The only actual difference is the success or the fail. Now, this is the same code, but it's been refactored to no longer violate dry. And what we've done is we've extracted that if-else logic into a reusable method in a new class. And this class is also implementing an interface or an abstraction. What this now actually means is that, one, our logging can be used across our entire API, but also it can be independently tested. The logging logic is no longer actually tied to those get methods. And this is really, really useful because something we're going to be going into later on is that when you've got that kind of if-else logic in your get methods, you're essentially tying yourself to testing that logic when you want to test the actual API logic. And now we're going to go through YAGNI. Now, YAGNI stands for you ain't going to need it. If you keep in mind our previous newly improved API and the new logging method, we've only kind of done it for success or failure. And the current requirements of the API are only for getting and retrieving something. And when writing the code, you might kind of feel like, oh, well, we know there's a chance that in the future we're going to want to upload something and have a post method. But that isn't our current requirement. And what would essentially violate YAGNI is adding logic for that post method. There's a possibility we might need it in the future, but we don't currently need it, so we shouldn't add it. And this if statement, where we're checking the HTTP method being a post, that is the violation. Because as our current requirements aren't for a post, by adding this logic in now, we're not actually saving ourselves any time, because that's an extra added complexity to the method, which means we'd also have to test that branch of logic. And we don't know what the requirements are. We don't know when the post requirement might come in, if it will ever come in. And it's entirely possible that it has completely different logging for that. Now, I'm going to cover solid later on, but for now we're going to go into TDD. And as it is about TDD and code craftsmanship, you might be thinking, well, where does TDD fit into all of this? Now, TDD, or test-driven development, is something that is a really kind of crucial thing to start kind of getting your head around. Now, Margaret Hamilton said, it's better to define your system up front to minimize errors, rather than producing a bunch of code that then has to be corrected with patches on patches. And ultimately, the code that was used to actually land on the moon for the first time did not have a single bug in it because she was so stringent about sticking to this philosophy. And that's really the heart of TDD. A key principle of TDD is test, then implement. And what that actually achieves is a better understanding of your requirements. It gives you confidence to make changes because you know that the behavior will still be correct. It ends up with clean and modular code, but also an increase in code and test quality. Because of the way that you write TDD, your tests essentially end up as documentation. And something that's really important is you get fast feedback and therefore less bugs. And what I mean by fast feedback is that by writing your test and then implementing it, you know straight away if there's any error in your implementation because you've already got that test there. Instead of the traditional way of writing the code and then writing the test, where you're not actually writing your test for your requirements, you're writing the tests to pass the code you've already written. Now, TDD, it's not just writing tests. Really, it's about thinking of the behavior and outcome before you write the code. Now, when working on any development tasks, the first thing that we as engineers or business analysts, or product managers do is we define the requirements. Is that way we know what we need to build. By writing our test first, we're actually doing the same thing. You need to really understand your requirements, and then you write the tests for those requirements. And by doing that, you're actually defining the behavior of your code before you've written it. And then once those tests have been written and they're failing, sure, but we know what we need to build. And this applies to every level of testing. And it can be anything from unit tests, which are when you test just the kind of one method or kind of a silo of business logic, to behavioral tests, which test the actual behavior of your service, to full system tests, which could be everything, including possibly the UI. In your handout, there's a link to the test pyramid by Martin Fowler, which goes into a lot more detail about different levels of tests. And ultimately, TDD is about changing the way you think when solving problems and approaching building something. It's about not just bashing out code as quickly as possible, but it's about really understanding your acceptance criteria and what are we actually getting out of adding this feature? What changes are we having to make? And making sure that the customer or the user is actually getting that behavior that they want from the beginning, because that behavior is defined in our tests, and that then influences the way that we write our code. Now, what does this actually look like? First, you add the test, and that could include classes and methods you actually haven't written yet. You then run the test, and this is really important. It has to fail. If it doesn't fail, it means you're not testing something new. You write the minimum code needed to pass. And this is something that I found quite hard to kind of do to begin with, because the code at this stage, it isn't nice code, it's ugly, it's verbose, it's literally the minimum code needed to pass your scenario. You then run the tests and they pass. And then step 5 is really important. You refactor, and you refactor with confidence, and you essentially just repeat the steps. And you do this until your code is in the state that you want it to be. And then you're done. Now, something as well is that you need to ensure that your tests cover all of the different scenarios that they need to cover. You know, most implementations will have, you know, multiple inputs. And as you add more and more test scenarios, you might actually need to just refactor your tests as well, because they may no longer be applicable. And I'm going to go through advanced TDD, or BDD, which is behavior-driven development. Now, this on the right is an example of BDD written in Gherkin. And Gherkin is kind of quite a common syntax for writing these type of tests. But ultimately, they're written in plain language. And they're essentially written by a business analyst or your acceptance criteria when you're told, I want it to do this, and then this, and then that. And what it actually does is it tests the behavior of the service in the same way that an actual user or client would be using it. And something that's really important is you write these tests before your unit tests. These are normally the first tests that you write and the last tests that will pass. And the reason that they're the last tests that will pass is because they will only pass when you've written your full requirement. So the entire service or function that you're adding has been fully implemented. Now, the purpose of these is that you're essentially ending up with a really clear executable specification, which means that you've documented exactly how your system is behaving. And because they come from your acceptance criteria, you have that confidence that you're going to be delivering exactly what was asked. And what about when TDD might not be possible? So you might have a situation where you've got something in production and you've got a bug and you have to get that fixed out right now. Or you might have a system where, there isn't the means to have automated tests. You can have legacy code bases that actually violate code craftsmanship, and that violation will make it really hard to write your tests first, which we'll kind of explain a bit soon. You also might have legacy code bases that actually rely on technology that just don't work with unit tests, such as something that doesn't support mocking. And for those who don't know, mocking is essentially faking behavior of an abstraction or interface. And the reason it's used in unit tests is so that you don't have to actually test the dependency of the interface. Now, how do we make TDD possible when it isn't? If you've got a production fix, as soon as it's done, you need to backlog a ticket and prioritize it, or just straight away implement those tests. Another thing in all scenarios is follow Boy Scouts. And as I mentioned at the beginning, Boy Scouts is leave it in a better state than you found it in, which essentially means refactor as you go and refactor both the tests and the code base all the time. need to, if you've got a system that doesn't support automated testing or a tech stack that doesn't, maybe, it's violating code craftsmanship and it's just really hard to add those kind of granular tests. Investigate, and this is really important, plan. How can you modernize your tech stack? How can you actually add those automated tests? Break it down into small chunks to be able to understand, okay, well, I would need to do this, which means I'd need to do that. And the planning here is really crucial. If possible, write your new features following TDD and code craftsmanship where possible in legacy systems. And this can be really hard because you're normally going against the grain. But if you're able to do it, it will be so incredibly beneficial because it will end up making your life so much easier in the future. And honestly, sometimes you just need to play around. You need to kind of see how much work am I going to have to do to retroactively implement the code craftsmanship principles, such as adding abstractions, and write your tests and follow the code craftsmanship principles. See if you can do it. And if you're able to do it, but it's going to be a really long process, document and plan. Talk to your team, find ways of having small, quick wins because they really help boost morale when you're having to essentially refactor a legacy code base. And some things to watch out for. There can be a misconception sometimes that when following TDD, you want every single line of code to be covered in tests. And that's actually not true. What's more important is having meaningful tests that cover the actual business logic. You need to always keep in mind that you might need to remove or refactor tests when they're no longer relevant and don't make sense anymore. And it's the same with badly written code. If you have tests there, then you can re-implement that code because your tests are there to make sure you're not changing the behavior. Something to watch out for as well is over-testing. So you can actually end up in a scenario where you have the same code tested multiple times. And this is something to watch out for because if you've got passing tests that cover the logic, you actually might not need to write more code or more complex code. Now, have someone else also review your test cases and make sure they're actually fitting your requirements and your acceptance criteria. Because we all have our own, we'll read something and we might have our own, ideas of what that means. Having another pair of eyes is always helpful. And the overhead of TDD. Now, adopting the practice of both TDD and code craftsmanship, it can take time. And like any skill, it takes practice. But once you get going with it and you get quicker at it, it will actually mean that implementing new things will be quicker as well, because your code base is going to be in that clean, maintainable, and extendable way. And what that actually means is it's easier to add new features. Another thing is that there might be situations you actually just don't need to do TDD because you might have, let's say, a tool that you've written quickly, and it's really just to help you for something, and it's not going to be used much. Nobody's going to be relying on it. The customers aren't going to be relying on it. It might be that the overhead there just isn't really not applicable, sorry. The overhead just might not be needed at that point. Now, a key part of writing TDD is writing granular tests. And the thing with TDD is that TDD and code craftsmanship, they really go hand in hand because by following the principles, you end up with small, easily testable methods. But also, by following TDD, you actually naturally end up writing small, granular methods that naturally lend themselves to code craftsmanship principles. Now, there was a lot to take in there, and I'm going to now hand you over to Farouz, who's going to do a live example and actually show in person these concepts.
Hello, everyone again. Hello, Mushkan, James, Dave, Alicia, Janet, Rosanna, Iona, and everybody else who is still with us. Thank you for being here. I'm going to share my screen. A second. Right. Okay. So during this session, we're going first look at this simple task that we want to code. Then we look at our acceptance criteria. Then we'll start our coding with writing a simple failing test. Technologies that I'm going to use during this practice are C# programming language, XUnit testing framework. You can use any testing framework that you're comfortable with. We'll use fluent assertion to assert our unit test, and we'll use and substitute to mark our objects. Right, Fibonacci sequence. How many of you here know what is Fibonacci sequence? I'm guessing a lot of you. It's a very fun to remember sequence of numbers. Fibonacci sequence is a sequence of numbers in which each number in the sequence is equal to the sum of two numbers before it. For example, in the sequence that's in the screen, you can see that 21 is equal to 13 plus 8, right? 13 is equal to 8 plus 5, and so on. The first two numbers in the sequence are exceptional. They don't follow the same rule, and they're called kickoff parts. Just notice that the sequence starts with index 0, similar to arrays and lists in most programming languages, right? And then if you're wondering what is index, it's the position of the number in the list. So the first number, 0, is index 0. The second number is index 1, and so on. Right, now our acceptance criteria. Our acceptance criteria is to generate Fibonacci sequence. Our Fibonacci generator should, when it's given index 0, return 0. That's the first number in the sequence, right? When it's given index 1, we want to return 1, and when it's given index 2, return 1. Given index 3, returns 2. And then given index 5, we want to return 5. These all are according to our sequence at the top of the screen. Negative indexes are not accepted. We want to cover that acceptance criteria. Our last two ACs or acceptance criteria are to practice solid principles and clean code. Right? Okay, so during our practice, first we write a red test. Then we write minimum code to pass our test and make it green. And then we refactor our code. We'll follow this circle until we don't have any failing tests to write, any more failing tests to write. Okay, right. Let's jump into the code. Okay, so you can see that I have an empty class, Fibonacci tests here. And I'm not going to create any classes or any object or any code. I'm going to start with writing a test. I've created this code snippet, which makes me write faster, type faster, right? Naming of your unit tests are very important because they act as a document for your codes. In our company, we normally start with name of the function that we want to test. I'm going to call our function getNumber. Condition that we want to set is given index 0. We should return. Right. And then our arrange and act and assert are three important steps of every unit test. In arrange section, you arrange your classes or object or anything that is required for your test. I'm gonna create a generator object of type Fibonacci generator. And yeah, we don't have this class yet, so my test is telling me, driving me to create this class, right? Creating the Fibonacci generator class. And then I'm gonna create a result by calling generator.getNumber. And I will pass index 0. So notice that this getNumber is the same name as I put at here, right? And then I use Visual Studio to create getNumber method for me. And my assertion will be result dot should be 0. Okay. So this is the simplest test that we can write. Given index 0, we want to return 0. That's the first number in the sequence. Now I'm going to click on this little circle at the left to run my test. And then I'm hoping that my test will be red. Ah, it is red. Now I have the red test, which is the first step in TDD, and then I write minimum code to pass my test. Minimum code to pass this test is just simply turn 0. You might get tempted to write some logics, that formula, everything. You have to stop. You just have to write minimum code here, right? And then I will run my test. You can see it's green. Okay, so we have red, green, and now refactor. For refactoring, I can see that the parameter that Visual Studio is created here doesn't have a good name. I'm going to rename that to index. And then I cannot think of any other changes here. Quickly going to go to my next test. So what would be my next test? Generating the second number in the sequence, right? Given index 1, I want to return 1. Right? And then passing 1 here and searching if the result is 1. On the test, that is red. Now, what's the minimum code we can write to pass this test? Minimum code is to return index, because in this way, the first test will pass as well. Let's run all of our tests, and they're all green. Now, we have red, green, and we want to refactor now. What is the best refactoring we can think of? GetNumber method looks tidy. We can't have any more refactoring here. But you can see that this line has been repeated in both tests, and that is against dry principle. Do not repeat yourself, right? I'm going to move this line of code to my class constructor. Move it here. This arrange part not required. And then I'm going to remove that from my second test as well. And then make generator a private field. Make it a private field so both my tests can understand it. And then one more change. I'm going to rename generator to target. Some developers, they call it SUT or system on the test. I normally call it target. It's more clear this way. Right? Now, we have 2 tests, but there is one more change that I'm going to make before moving to my next test. And that is combining those 2 tests to one. You can see that most testing frameworks do support parsing inline data. And you can parse index to an inline data and look at the name of the unit test. It's given index 0 and 1, it returns index. It's more maintainable and looks better as well. Right, now what is our next failing test? Our next failing test is to create the next number in the sequence, which is given index 2. We want to return 1. That's this number. And then we pass 2. We expect it to be 1. Now I'm going to run the test. Now it is red, right? What is the minimum code to pass all of our tests in this stage? Is if index is less than 2, and return index. Otherwise, simply return 1. You can see that here I expect 1, right? And then run my test. It is green. To make sure I'm going to run all of the tests, and they're green. Right. Is there any refactoring we can do at this stage? I cannot think of any refactoring. Let's quickly move on to our next test, which is given index 3, return 2. Right. Let's run the test. It is red. Now, the simplest code to pass all of our tests is just simply change 1 to index minus 1 and then run our test. It's green. I'm going to combine these 2 tests now in the refactoring part. I'm going to combine these 2 tests to one test and then pass index and result from inline data. It will look like this. Even any index more than 1 returns expected result, and then I will pass index and result through inline data. Let me run all of our tests, and they're all green. Right. What is our next failing test that we can write? Right. Simply, I'm going to add it to this inline data here. Well, if you pass 4 and then 3 here, it will be green because it follows the same rule as the other ones. Let's run it. It's green. Our next failing test will be the number after that, this 5. So if you pass index 5 and you expect result 5, it will be red this time. Okay, what's the minimum code to pass all of our tests are get number with index minus 1 plus get number index minus 2. Right, it's crying because it doesn't like the type we're returning here. And now running our tests, all green, running all of them from here to make sure we haven't broken the first ones, and it's all good. And then our method is looking quite similar to our Fibonacci formula, right? Okay, one more test, and that is to cover our negative paths, negative indexes are not accepted. And then for that, we will assert if given negative indexes, it should throw exception. For throwing exceptions, just notice, because get number is going to throw exception, right? It's not gonna return any result, so we cannot assert it by result, but we can make an action. I'm gonna call that action, and that action is running get number. Okay, and then my assert will be action dot should dot true exception of not supported. A supported exception. That's the one I like. Okay, now I have a test, and hopefully it will be read because we haven't written any code yet. And then in our get number to pass our test, the minimum code will be if actually this has to be a negative number. And it will be read again because we are not throwing exception. Problem is, all right, to pass that, we'll check if index is less than 0, and I will throw a new not supported exception. That's what our test is expecting. Right, and then running my test. It's green this time. So running all of our tests, it's all looking good. Okay, I have 2 more acceptance criteria that we want to code. But before that, we would need some knowledge of solid principles. I'm going to cover some of these principles when I'm coding for those 2 acceptance criteria. And then Sarah is going to take you through solid principles. There are some of them are a little bit complicated, but I cannot emphasize enough how important they are to learn and to use in your code. Pass it to Sarah now, and then come back here and we code again. Okay.
Hi everyone, let's go through solid. See, great. Now we're going to do an overview of solid. In the handout, there are a lot more examples of both violations and fixes of solid, including in C#, Python, and JavaScript. So if this is all going over your head, please do refer to that handout because there are a lot of resources on there. Now, the S in solid, and it stands for single responsibility principle. Now, Robert Martin said there should never be more than one reason for a class to change, and that every class or method should be focused on a single concern and to not couple logic that has different responsibilities. And for those who don't know, coupling is essentially dependency. Now, imagine that you have a method and it produces a document with formatted data on it. This can be changed in 2 ways. The data can change, but the formatting can also change. And they can change for different reasons. Therefore, each concern, i.e. the data and the formatting, should be in its own method. This way, they can be actually independently changed and tested. And this independently being tested, brings us back to TDD, because you don't want it to be that you have to change, let's say, where your data is coming from, and that then having a cascading effect where instead of having to change it in a few small places and change a few tests, you suddenly have to change it everywhere. Now, the open-close principle. Bertrand Meyer said that software entities, such as classes, modules, and functions, should be open for extension, but closed for modification. And this is something that can be quite hard to get your head around. But essentially, a module is open for extension when it's possible to add fields to the data structures it contains or new elements to the set of functions it performs. And on the other hand, it's closed when it can be used by other modules. And it assumes that the module has been given a well-defined, stable description. Now, that well-defined, stable description, particularly in C#, but in most languages, means using interfaces and abstractions. Because if you remember, an interface is essentially a contract or a well-defined description. Some other ways to do this is things like polymorphism or a common design pattern such as the strategy pattern. And the strategy pattern is essentially the runtime figures out which version to actually run. And there's more information on this in your handout. What this actually means, though, is that we want to write code that you can easily add new functions to when we need to, but you don't have to change the existing code when we add those new functions. You only need to change that existing code if, unfortunately, a bug is found. Now, Barbara Liskov and Jeanette Wing invented the Liskov substitution principle. And what they said was, if S is a subtype of T, then objects of type T in a program can be replaced with objects of type S without altering any of the desirable properties of that program. And you can essentially replace an instance of a class with a more specific instance of the class, i.e. a subtype, without changing the behavior or causing errors. And that's really important there. It also means that new exceptions can't be thrown by the methods in a subtype, unless they're subtypes of exceptions thrown by the method of the supertype. Now, that bit is a bit more kind of complex to get your head around, but the really important thing to keep in mind is just being able to replace an instance of a class with a more specific type. Now, when I was first learning about this, I found it really hard to get my head around. And an example I've kind of come up with for you guys today is, let's say you've got a dog class, and a dog can walk, they can wag their tail, and they can bark. A dog is T, it's the supertype. You then create a subtype, puppy, and when I tell the puppy to walk, it walks. When I tell it to wag, it will wag its tail. But when I tell it to bark, I instead get burnt to a crisp, because instead of barking, they breathe fire. This is violating the Liskov substitution principle, because the puppy, i.e. the subclass, has contract breaking behavior. We have ultimately altered the properties of the program because I have a puppy and it doesn't go woof. It's instead some weird puppy dragon hybrid. And something that can be kind of hard with this is a lot of the time with a lot of kind of modern IDEs, on the very kind of top level, they might not actually let you violate Liskov because they have type checking. However, with languages that aren't as strongly typed, this is a really important thing to keep in mind. And by really following this, it makes life so much easier. Now, the interface segregation principle essentially boils down to saying many client-specific interfaces are better than one general purpose interface or abstraction. A class should never be forced to implement an interface that it doesn't use, and a class shouldn't be forced to depend on methods that they don't use. So to achieve this, it's essentially split your interfaces or abstractions that they're not granular currently. They have a lot of kind of things going on in them into smaller, more specific ones. Going back to the S and solid, ensure that the interface has a single responsibility. And keep things decoupled, i.e. not have too many dependencies, because it will allow for easier changes and more tests. And it essentially really supports the open-close principle. And finally, the D in solid is dependency inversion principle. And what this means is depend upon abstractions, not concrete types. So have as many classes and methods as possible, relying on the interfaces and abstract types, and write classes and methods that aren't dependent on each other as much as possible, but specifically aren't dependent on concrete types. And this means that you're going to end up with code which you can change a lot easier. You can add to it. You can add that new feature, that new functionality without it being a nightmare. And it also means it's a lot easier to test because you can mock, i.e. faking, the interfaces. So this comes back to TDD in the sense that you can test the method without testing its dependencies. But ultimately, solid is actually part of Codecraftsmanship. It's not inherently part of TDD, but as hopefully you're seeing, they are essentially two sides of a coin because of how much they overlap. Now, solid can be really hard to understand, but luckily Farouz is actually going to show you in real life how to implement and follow these principles. Over to you.
Thank you, Sarah. Let me just share my screen quickly. Right. Okay. Our last two acceptance criteria. When an index is given to our Fibonacci generator, we would like to log the given index to a file. That is the next AC we want to cover. And then what do we do to start with that, to start covering that requirement? We will write a failing test. Right? When any index logs to a file, that's the test. And then our act is target.getNumber and index. But how do we assert that? How do we know that getNumber has written to a file? I'm going to use interfaces here. And then I will explain why I used interfaces. Creating, I would need a iFileLogger interface. You can see that my test is telling me to create this interface. Quickly create that in Logger folder. Right. Now I have iFileLogger. And then in my assertion, I will assert that iLogger has received a call to a method called log when the index is the same as what we have here in getNumber. And you can see that log doesn't exist, the method called log. I use Visual Studio to create the method. Log Now we have it here in our file logger. We have a method called log, and then I will run my test. And hopefully it is red. Yep, we have a red test. What is the minimum code to pass that test? Going back to our get number method. Now, why did I use interfaces at all? What are the options I had to log to a file in Fibonacci generator? Well, maybe it comes to our mind that we simply write to a file in our get number method, right? But that is against single responsibility principle of solid principles. Every class should only have one responsibility. In here, Fibonacci generator is writing to a file and also creating the Fibonacci sequence. Cannot do that. But how about we move the writing to a file to another object and then call that here like something like file logger, and then log it to a file using file logger object. How about that? That is against dependency inversion principles. Our file is not, our class should not rely on concrete classes. We have to rely on abstraction and interfaces. So now let's use our iFile logger that we have created, right? Go back and maybe now iFile logger, and I'm gonna use Visual Studio to create that for me. And then instead of relying on this concrete file logger class, I will use my interface, our file logger, and then I'll call the method log, passing index. Going back to my test, run it. Oh yes, so another important step that I forgot to add is mocking file logger and passing to my Fibonacci generator. Then how do we mock objects? And substitute, you can mark it this way and passing it to Fibonacci generator. This part that I'm injecting or passing file logger, if you're not that much familiar with, I suggest you read about inversion of control or dependency injections to learn more about what I'm doing here. So basically, whoever is going to call Fibonacci generator has to pass an object of file logger over for Fibonacci generator to be able to work. Now going back to my test again, running, now is green. Okay, how about my next acceptance criteria, which was logging to a database, right? Test for that, as you can guess, is given any index logs to database, and then we call get number, and then for assertion we again need another interface for database logger. Let me quickly create that here, and we don't have a database logger yet. Creating it in a logger folder and a new interface. Go back to my test, and then I will assert if database logger has received a call similar to what we had here, a log method, which doesn't exist yet, and then I'm creating it. Cool. Let's run our test. It should be red because we haven't written any code for that yet. Back to our get number method. We need that iLogger property field, database logger field, then pass that through our class constructor, right? Then in my get number method, I will call database logger.log with our index. Go back to my test. Oh yes, you can see I have to mark our database logger again here. That is expected to be passed through our Fibonacci generator class constructor, right? Let's pass it through and then run our test. Hopefully it will be great. It is great. Right. Now for refactoring part. You can see here that for adding a database logger, I had to come and change Fibonacci generator, add a new interface, and then change get number to call the log on database logger, right? Solid principle open close is suggesting us to make our classes designed in a way that they are close to modification and open for extension. That is going to help us here. We will change our Fibonacci class in a way that for the next logger that we want to add, we don't need to change this class anymore, and we don't need to change get number anymore. How do we do that? We'll create a generic logger. I'm going to call that iLogger. Which has similar method, right? And then instead of passing different type of logger, I'm going to pass a list of iLogger interface here, right? And then I'll call that loggers, removing all of these that are not required anymore. And then I will introduce a field for my loggers. And then for each iLogger, for each logger that I have, let's call it logger to have more generic name. We'll call logger.log with the index passed over to it. All right, now look at this class and compare to how it was before. For any new logger that you want to pass to Fibonacci generator, you don't need to change Fibonacci generator class anymore. All you have to do is inject the logger. As long as they implement iLogger interface, then Fibonacci generator doesn't care which type of logger you pass in. You can replace your file logger, database logger, cloud service logger, any logger that you want in the future. You can just pass over, and you don't need to make Fibonacci generator any. You don't need to make any changes in Fibonacci generator anymore. But how about our tests? So we don't need these two interfaces anymore, right? Because we're going to use one interface of iLogger. But how about our tests? They're going to break now, and it's okay to remove some of your tests or change it as long as it makes your code better and cleaner. Okay. And then how does it change to around new changes? How do we change our test? I'm going to create a loggers property here instead of these two. I'll create one loggers property of type list of iLoggers. And then I will create a mock for iLogger. I'm gonna call that file logger and database logger, and then add that to my list of loggers, and then inject it over to Fibonacci generator. Okay. And then I will change my test to given any index logs to all loggers. Okay. Then we pause. When we call our get number, we will assert that for each logger in our loggers collection. I will receive a call to its log method. Running the test. Oh, it's green. Cool. Look at our test. All the acceptance criteria are covered now. And then our code looks quite clean. And we have followed solid principles to write this code. I'm pretty happy with that. Right. Now, I'm going to leave you with two very good books. If you want to read more, there's this book, Codemanship, TDD by Jason Jorman, and Clean Code by Robert C. Martin, which I strongly recommend you to read. There are lots of links and resources for further reading in your handout, plus more examples in different languages. There's also a full interview with Margaret Hamilton discussing her work as the first female software engineer. Talking about Margaret Hamilton, listen to her advice for women getting into programming. Don't let fear get in the way, and don't be afraid to say, I don't know or I don't understand. No question is a dumb question. Now we have around 10 or 15 minutes to answer any question that you have. Otherwise, thank you so much for joining us today.
Thank you both very much. That was amazing. As Bruce says, if you've got any questions, obviously let us know now. I know there are a few people who have been watching our sessions retrospectively as well. So if you are, I believe Sarah is on the Discord channel and will continue to be on the Discord channel. So any questions you can obviously fire in general as well if you're watching this back. But yeah, if there are any for now, feel free to let us know. But a big thank you to you guys, Sarah and Farouz. That was great, and thank you for giving up your time to get involved.
No problem. And I was just going to say, in the chat, there's also the link to the GitHub, which now has all of the code, all of the slides, and the handout on there. And people can also ask questions on there as well. Yeah, and again, we kind of talk about the Discord channel. We'll have like a useful resources section on there as well tomorrow. So all of this stuff and all the links and everything will be posted on there. So you can kind of look back on any of it if you need to. But yeah, thank you both so much. And also there was a shout out at the start for the Dojo hoodies, I think. And I just want to big those up again because yeah, they're looking good. There you go. In sync. I promise that wasn't rehearsed. But yeah, I think a big thank you to everyone. I'm not sure whether or not there are going to be any questions streaming through. We'll give it another minute or two. But as I say, anything retrospectively as well. And if you give this a go, I think, we'll go through, I won't reveal too much ahead of time because we'll be doing prize announcements tomorrow and theme announcements tomorrow. So no spoilers ahead of time, but Dojo are going to have their own prize category, and this session will help with that as well. So if you kind of have any questions after the sessions tomorrow or anything, then again, just let us know and we'll be here for some support. So thank you all very much for tuning in. Thank you both very much for being a part of it. Enjoy your evening, and there's now less than 24 hours until the hack begins. So
yeah, get thinking, everyone. I'm looking forward to it. Thank you. Bye-bye.
Thanks.